next talk is on learning to prune, speeding up repeated computations by Ellen Wittachek.
Thank you. So this is joint work with Daniel Alavi, Adam Kalai, Katrina Lidget, Karen Musco, and Chrisos Samos. When I was growing up in a beautiful place called Lincoln, we used to go to a city called Burlington all the time. And there were a couple of routes that we used to take, but there were also a lot of windy dirt mountain roads that we knew would never ever be in the shortest path. But if we were to run Dijkstra's algorithm to figure out how to get from Lincoln to Burlington, Dijkstra's algorithm would have wasted time on those muddy mountain roads. In this work, our goal is to solve a sequence of similar problems using learning while exploiting common structure that those problems have. So for example, these problems might be routing problems that a commuter faces day to day. What we notice in these repeated computations is that oftentimes there are large swaths of the search space that never ever contain optimal solutions. So our goal is to learn how to ignore them. And we see this structure in problems beyond shortest path routing. So for example, maybe you're solving a sequence of linear programs with the same constraints but varying objective functions. You might find that only a handful of LP constraints are the ones that actually bind most of the time. Or maybe you're doing string search and you find that only a small portion of your DNA strings ever contain patterns of interest for your particular application domain. So a little more formally, in our model, there's some function f that maps problem instances x to optimal solutions y. Our learning algorithm receives a sequence of problem instances. So for example, maybe each xi here represents the edge weights on some fixed graph or some fixed road network. And these edge weights vary day to day. So our goal is to correctly compute this function f most of the time while minimizing runtime. So in our model, a worst case algorithm would just compute this function f on each round. But we assume that we have access to other functions also mapping problem instances to potential solutions, which are faster to compute. And they're defined by subsets or prunings S of some universe U. You can think of this universe U as representing the entire search space. And we'll denote the function corresponding to a pruning S using the notation fs. So this function fu corresponding to the entire search space equals that true function f that we're trying to compute. So just to give you an example, maybe this universe U equals all of the edges in some fixed graph, and a pruning S equals some subset of these edges. So if you're to compute f of S, you would be basically looking for the shortest path restricted to edges in the set S. We're going to assume that there exists for every problem instance X a minimally pruned set S star of X. And basically what we're saying is that for any set S, fs of X equals f of X, the true solution, if and only if this minimally pruned set is a subset of the set S. So for example, you can think of S star of X as being the shortest path in the graph. Okay, so here's our algorithm. We're gonna maintain a prune set throughout this algorithm, and we're gonna initialize it to be the empty set. On each round, we're gonna receive a problem instance, and with probability 1 over square root of j, we're gonna explore. And that means that we compute the true solution, fxj, we compute the minimally pruned set, S star of xj, and we add that to our pruned set. Otherwise, we're going to exploit, which means we output the solution constrained to our prune set, and we don't update that prune set. So just to recap, at each round j, we're going to compute a function fsj of xj, where the set sj depends on the first j inputs. And so this sj is either going to be the entire universe or it's going to be our prune set. And we have a couple of goals. The first is to minimize the size of this set sj, because in our applications, computing the function fsj is the runtime. It basically grows with the size of the set sj. And what we prove is that on expectation over the random choices of our algorithm, the average size of the set sj is upper bounded by a set S star and a term that goes to 0 as the number of rounds grows. And this set S star is the union of all of the minimally pruned subsets. So you can think of S star as being the smallest prune set you could have used to compute the correct solution on every round. So this is kind of like a regret bound. And the proof is really straightforward. So let's think about what the expected size of one of these sets sj is. Well, with probability 1 over square root of j, we explore, which means that we compute the function fu. And with probability 1 minus 1 over square root of j, we exploit, which means that the set sj equals our prune set. And by definition of the set S star and the way that we create this prune set, we get this inequality here. So if you basically rearrange terms, you'll get our theorem. We have one other goal, which is to minimize the number of mistakes. And these are rounds where fsj of xj doesn't equal the true solution f of xj. We prove that the expected number of mistakes we make is upper bounded by the size of this aggregated minimally pruned set divided by square root of j, or square root of t. And in the interest of time, you can come see our poster for the proof sketch. It's a little more subtle than the previous proof. And I wanted to give one example of some experiments we have in this paper. So in this picture, the goal is to get from the top star to the bottom star. And so we run our algorithm on each round, taking the true length of these edges in this map of Pittsburgh, and we kind of randomly perturb all of the edge weights. And so the gray nodes there are the nodes that Dijkstra's algorithm would have explored, and the black nodes are the nodes in our minimally pruned subset. So you can see that our algorithm does prune down to a pretty small set compared to what Dijkstra's algorithm would have explored. And our algorithm only makes a mistake on the minimally pruned, or makes a mistake on computing the shortest path 7% of the time. So in conclusion, we provide an algorithm for quickly solving a series of related problems. It learns to prune irrelevant regions of the search space. With high probability, it makes few mistakes, and as we saw, it can prune large swaths of the search space. So thank you. Yeah, so that's kind of encoded in this set S star, which is basically the aggregated over all of the time steps, the minimally pruned set you could have used to correctly compute the solution. So if you're
I want to know which situation this can be applied.
Yeah.
Some kind of general idea of what related construction.
Right, so if your problems are all very related, like you'll have, let's say the shortest path is gonna stay the same on all of the time steps, then this set S star is gonna contain just a single path, so it's gonna be really small. But if your shortest path varies wildly at each round, this S star is gonna be maybe the entire universe U. So that kind of like, since our bounds depend on the size of S star, that encodes the relatedness.
While the next speaker sets up, maybe there's time for one more question. Is any? Okay. If not, Oh, okay. Jamie has a question.
Do you suspect that the size of a star is the right thing? Like, I understand that the rest of that, but is that the right relation of similarity that it
We don't have a lower bound that depends on the size of S star, so I think it would be cool to see some kind of like trade-off between mistakes and size of S star, or something like that. Yeah. Yep.
Can you weigh mistakes by how close you are to the optimization?
Yeah, that's another thing is we don't take. Maybe you are almost on the correct path, but we don't take that into account either.
Okay, let's thank the speaker again. The next talk is on fast determinantal point processes via distortion-free intermediate sampling by Michal Derezinski.
Thank you. So I'll be talking about algorithms for determinantal point processes. So let's first sort of motivate and define the problem. Right, so in the broadest terms, we're motivated by the question how to select a small representative sample of data. So this, as you might imagine, has applications in various settings in sort of machine learning and outside of machine learning as well, search and recommendation, text summarization, even sort of other settings such as Monte Carlo integration, experimental design. And so to make the problem slightly more concrete, suppose we're selecting out of a subset of n d-dimensional vectors, which we sort of pose as this matrix, n by d matrix X. We want to select a small subset. So now, straight off, there's the definition of the determinantal point process. So essentially, we sample a subset, and the probability to each subset is assigned to be proportional to this determinant constructed based on the sort of the submatrix based on the rows that we selected. So one thing to note is we're sampling out of all of the subsets of the data, and sort of the cool motivating property of DPPs is that even though this is sort of a combinatorial distribution, it has a closed form normalization constant. And in some settings, we want to only sample from a fixed size subsets, and that also can be done. Right, so in the settings mentioned above, in some cases there's actual theoretical guarantees that show that DPPs can very effectively be used for this problem. There's concrete guarantees. In other cases, they just work well in practice. And just to give you some intuition of why the sample selected will be representative, so essentially the connection here is between the determinant and the volume. So essentially the determinant that the probability is proportional to is the volume squared spanned by the vectors that we select. And so in a picture, right, if we have two vectors, that means we're looking at the volume of that parallelogram. And as we can see, if the vectors are not very diverse, if they're very similar to each other, then the volume will be small. So that's how we're sort of favoring diversity, and that makes the sample more representative. So now, what are the algorithmic challenges with sampling from DPPs? So first of all, it's not obvious that this can be done in polynomial time, but that has been shown. But still, there's certain bottlenecks. First one is as expensive pre-processing steps. So that typically involves exact SVD decomposition of the whole data matrix X. And the other sort of bottleneck is when we want to sample repeatedly from this distribution, which is needed often in practice, the cost of each sampling scales with the size of the entire data rather than the size of the subset we would like to sample from. In addressing this problem, in the existing literature sort of runs into those trade-offs between accuracy and runtime in the sense that we can either come up with exact algorithms and pay the expensive cost, or we can come up with approximate algorithms, in which case it's sort of often difficult to sort of say how approximate are they. So I'll right now select a very small representative sample of the related work, and so the sort of the classic result here by Hugh, Krishnapur, Perez, and Virag is an exact algorithm which indeed uses SVD decomposition of X, which costs ND squared time, and they propose this nice bottom-up sampling algorithm which essentially draws one point at a time and has to update the sort of probability distribution of each next point being sampled because it's a joint distribution. So that's why this is sort of still relatively expensive but cheaper than the SVD decomposition. So to summarize, the cost we pay is when we receive the matrix X, the first sample we draw, generally the cost we pay is for the preprocessing, which is the SVD, and the second sample we draw, we only have to pay for the sampling cost, which is here, and K squared. K here represents basically the subset size. So another approach that was designed to address the problem of having to compute the SVD decomposition is to use a approximate sort of sampler with a Markov chain whose stationary distribution is the DPP, or in this case KDPP, and so the key result showed that a very natural simple Markov chain is in fact mixes fast, and they showed Anarigaran and Rezai showed that it converges to with an epsilon total variation distance of the true distribution. And here, the cost of every sample is the same. It may be less than the SVD, but it's still somewhat expensive because we have to converge every time. We have to converge again with the Markov chain. So now, okay, so this is the prior work. So let's talk about the main result. Okay, so let me sort of parse this quickly for you. So basically, given a matrix X and some additional approximately pre-computed quantities, we have an algorithm that samples from a DPP in time. So if you have order d cubed k. So the remarkable thing to note is that there's no n in the runtime here, right? Which was there in all the previous cases. And to look at the guarantee, there's this raw term. Essentially, the algorithm samples from the DPP of X, but the X might be slightly rescaled, which is sort of a strictly stronger guarantee than the one, for example, given by the MCMC, the total variation distance guarantee. So, of course, to sample the first sample, the S1, we actually have to compute the approximate quantities, right? This is, so I sort of describe them on a high level as the computing a subspace embedding and computing the ridge levered scores. You may be familiar with those terms. Those are standard terms, and there's a standard methods to actually approximate them. And this can be done in sort of input sparsity time, so essentially linear time in the size of the data. And after that, for each next sample, we only have to pay the cost of the algorithm, which is independent of n. So just to quickly go over the main idea, the distortion-free intermediate sampling. The idea is to essentially, before we sample the target subset S, we're going to sample a bigger intermediate sample sigma in a very particular way so that we can downsample the subset S. But the crucial property that we will achieve, which is sort of maybe surprising, is that the intermediate sample does not in any way distort the distribution of the target sample. So what that means is that essentially every time we draw a new sample S, we're going to first sample a sigma, then we sample out of that, we sample an S, and it's as if we never sampled the sample sigma because it's distortion free. And so to do that, we propose this regularized determinantal point process. So I will not have a chance to get into the details, but so here is a definition. There's, of course, more details at the poster. Essentially, there's this identity matrix that regularizes the determinant, and the key sort of result we obtain is that this RDPP is a distortion-free intermediate sample for DPP, and this is sort of a more general approach that could be applied to other distributions than DPPs potentially. And of course, also we have to show that this is efficient. This can be efficiently sampled from, so I will not discuss that here. But to summarize, we show here that we can sample from DPPs with input sparsity time preprocessing and sampling time that does not depend on n at all. And so, yeah, for more details, come to the poster. And if you're interested, there's a follow-up work by me, Daniela Calandriel, and Michal Walko, where we sort of extend the results to kernelized DPPs and make some additional improvements. Thank you. It is stronger in the sense that, so in the paper, if you look in the paper, I essentially show that, so I show this guarantee that I showed here, and I also show that it implies a total variation distance of epsilon as well. So in that sense, you know, it implies this guarantee, but also it's sort of more useful in other settings.
Any other questions? Not. Let's thank the speaker again. The next talk is on a rank one sketch for matrix multiplicative weights, and Yair Carmen will give the talk.
Hello, everyone. So we're going to follow up on the theme of getting rid of those pesky SVDs. This is joint work with John Ducci, Aaron Sidford, and Kevin Tian. And the problem that we'll consider today is a matrix analog of the very fundamental problem of online learning on the simplex. Applications for our matrix extension include online PCA and semi-definite programming. So like in every online learning problem, we play a game in stages, and at stage xt, we take an action, at stage t, we take an action xt, which is a matrix, a symmetric matrix. And this matrix is in a set called the spectrahedron, which is a set of positive semi-definite matrices with trace 1. And this is the natural matrix analog of the simplex, because if you think about the eigenvalues of a matrix in the spectrahedron, it's positive and it sums to 1, so it's exactly on the simplex. And an adversary is also going to give us a symmetric matrix. We're going to call it GT, or the gain, and it's going to be on the spectral box. So the eigenvalues of GT will be inside the box. And we earn a reward, which is the inner product between the gain that we got and the action that we played. And as always, our goal is to minimize the regret. So we want to make sure that the difference between the best single action chosen in hindsight and all of the rewards that we got is not too large. And because it's the spectrahedron, we have a closed form for that supremum over X star. It's just the maximum eigenvalue of all of the gains that we've seen. And if you give me an algorithm that makes the regret small, it immediately implies an algorithm for online PCA, and it implies an algorithm for semi-definite programming. So one algorithm that makes the regret small is called matrix multiplicative weights, also known by matrix exponential gradient and spectrahedron mirror descent. And it's the direct matrix analog of standard multiplicative weights. So we will sum up all of the gains we've seen so far, we'll multiply them by a step size, then we'll exponentiate. If we were exponentiating a vector, now it would be a positive vector. Since we're exponentiating a matrix, it's going to be a positive matrix. So we're going to normalize it to have unit trace by dividing by the trace. The bad news is that unlike exponentiating a vector that costs time O of n, exponentiating a matrix costs time O of n cubed, exactly because we need to do this eigen decomposition in order to exponentiate a matrix. And this is the problem that we want to solve here. We want to have cheaper steps than this. But let's first say what's good about matrix multiplicative weights, and what's good is the regret. So for any adversary whatsoever, we get the same regret guarantee that we get for multiplicative weights, and it's optimal up to constant. This means that if we look at the total computational cost to make the average regret less than epsilon, it's going to scale as 1 over epsilon squared, but also scaling with n cubed, which is what we want to solve. So now let's describe the sketch that we propose. So one way to think about our sketch is it's essentially a rank 1 JL sketch. It means that we start by sampling a Gaussian vector UT, and then we take this Gaussian vector UT, and we multiply it by the same exponential matrix for multiplicative weights, and then we take the rank 1 matrix formed by the result we call it VT, and our action is XT. So in terms of computational complexity, the big win here is that we don't have to exponentiate a full matrix anymore. We just have to compute the product of a matrix exponential and a vector, and we can do this efficiently with the Langchus method by just a small amount of standard matrix vector products. So this will never take much more than n squared, and it can be much less than n squared if the matrix has structure. And additionally, the actions that we play have rank 1, which means they're much cheaper to store, but it's also a complication because we don't really have a hope anymore of competing against an arbitrary adversary, because that adversary can choose a gain orthogonal to the xt that we played, and then we will have very high regrets. So we add an assumption. We assume that the adversary chooses the gain simultaneously with us choosing the action xt, or more formally, that conditional on all the past, the gain is independent of xt. Another way to look at it is just saying that this randomness we use to create ut is private to us and the adversary doesn't see it. So this is a fairly weak assumption. It's weaker than an oblivious adversary, for example. And under this assumption, what we are able to show is exactly the same regret guarantee of matrix multiplicative weights, but on expectation, and with slightly larger constants. On top of that, we are able to show high probability regret guarantees, and also a relative regret bound like there is for multiplicative weights. So the bottom line is that now the overall computational complexity to get epsilon average regret scales with epsilon a little bit higher because of the Langchus iterations, but it scales with n squared instead of n cubed. So when n is large, this is certainly a computational win, and remember that actually we are going from eigendecomposition to matrix vector products, and when the problem has structure, matrix vector products will often be much cheaper. So this is all our results in one slide. Now, let me mention that previous work also works on reducing the complexity of matrix multiplicative weights. Unfortunately, I don't have time to go through them one by one. I'll just mention that compared to the best previous results, we improved the complexity by a factor of log n to the power of 5, and that our regret guarantees are optimal up to constant. We also have a few new analysis techniques that I would like to share a little bit. So really the key for our analysis is to take the dual averaging point of view of online learning. And from a dual averaging perspective, the only thing that defines a procedure is how you map from the space of linear combinations of gains into the space of actions. So in our case, gains live in symmetric matrices and actions live on the spectahedron. And what matrix multiplicative weight does is map them through this mirror projection, which is the exponential divided by the trace. Now you can just view our sketch as taking this projection and replacing it with something else, but something that is random. So for every vector u, we'll have a different mirror projection pu that maps from symmetric matrices to the simplex, and then we're going to pick a random Gaussian u. And now an important observation is that since we just want to sum the expectation of the rewards, which are inner products, it's actually enough to look at where do these randomized mirror projections take you to on average. However, there is a challenge because the point that they take you to on average is not the matrix multiplicative weights projection. So what we do is we just define a new mirror projection function, a deterministic function p bar, which by definition is the average point that our sketch takes you to. And now what we're going to show is this is a perfectly good mirror projection to do dual averaging with, in the sense that the actions x bar generated by these projections also have a very good regret guarantee. And since our xt is an unbiased estimator for x bar, we immediately get the same regret guarantees for xt, which is what we want. So what do we need to do in order to show that a p bar is a good mirror projection? It turns out we actually need to show very little. We need to find a little p bar, which is such that p bar is its gradient, and then we define a Bregman divergence. And then we show 3 geometric properties of the, of the Bregman divergence and p bar. So first of all, smoothness, which you can think about as p bar being Lipschitz continuous, or little p being smooth, or the divergence being bounded by a squared norm. And then a diameter bound, which is similar to the range bound from follow the regularized leader. And then surjectivity. So you can get to every point in the interior of the simplex by mapping some symmetric matrix with p bar. Only these 3 properties are enough to show the regret guarantee that we want. So if you play actions x bar, you get exactly the same regret guarantee that we claimed in the beginning. And now xt, since it's unbiased for x bar, immediately gets the same regret guarantees on expectation. And we think this idea might generalize to other settings where you have a set that is expensive to project to, like positive semi-definite matrices, and you have an idea for like a cheap random thing you could do in order to do this projection. So one framework of looking at it is just define the average projection and analyze it. Now, I would like to point out that the average projection is as expensive to compute as matrix multiplicative weights, maybe even more, but we have a cheap unbiased estimate for it. So how we show these geometrical properties, unfortunately, I won't have time to go into. The short answer is spectral function analysis, and it allows us to basically tie together matrix multiplicative weights and our sketch that we created, and this way kind of piggyback of all of the nice properties of matrix multiplicative weights. So to summarize, we found a cheaper way to do matrix multiplicative weights. We had to add an assumption about the adversary, but even with this assumption, it's applicable to online PCA and semi-definite programming. However, other applications like online convex optimization will be limited by our assumption. Nonetheless, we think that this technique might be helpful in other settings as well. So you're welcome to the poster. There's also the paper on archive. Thank you.
We have time for one question while the next speaker sets up. Daniel.
Yeah.
Depart from sort of the mere descent to the regularized? I mean, if you take the, I guess, potential pool of whatever thing.
Yeah, so that's a good question. So for matrix multiplicative weights, both kind of approaches are the same. For our randomized thing, it's not clear if you could take our p bar, right, or little p bar, do the dual, and follow the regularized leader with it, theoretically. It might be a different procedure, and you won't necessarily have an unbiased estimator for that.
Manfred has one more question while we set up the next one.
Do you know how much variance is produced by this method?
Yeah, so that's an excellent question about the variance. So kind of the magic is that all of the variance get eaten up in the other term for the regret, like stochastic gradient descent. The variance is at most 1 because the size of the spectrahedron is 1. Other than that, I don't have much to say about the variance.
Let's thank the speaker again. The next paper is on corsets, discrepancy, and sketches in machine learning, and the talk will be given by Igor Liberty.
Hello, good morning. So this is work done by me and Zohar Karnin, who's a principal scientist at Amazon and a good friend. I'm going to jump right in. I'm going to give a lot of references in the end. We don't have time to actually dive into a large body of work on corsets and epsilon approximations for data. But the basic idea is to have, when we have a set of points, they could be either samples or just like arbitrary data points, we want to create a corset for them. And by corset, I mean in the sense here that there is some function that I'm going to sum over data points and some set of model parameters or some query, and I want this to be similar on the original data and the corset. And so if I look at the Gauss, like some kernel density, I can think about summing up my points with some diminishing weights around some point, and I want that measure to be the same approximately on both sides, no matter where I center that ball. And of course, you can think about a measure being like roughly half the space with maybe some smooth transition. And if this is correct for all, say, half spaces, then I can create a corset for, say, my positive and negative examples and do like some training on the corset instead of on the whole data. And a very natural question to ask is how small can those corsets be, and what problems kind of lend themselves to this kind of treatment. So I'm going to start with something, kind of an exercise to go through this, kind of to construct something together. And we're going to look at a very simple space. It's just numbers, so x1 to xn. And we're going to look at the function. It's just the sum of these step functions. So this gives you the cumulative distribution of those points, right? So my function is just a sum of step functions where the step is at xi. And I want to approximate this. And an epsilon approximation for this is any function that's, wiggles through between those, two dotted lines, epsilon n away from the real function. And the way I'm going to try to do this first is I'm going to just skip every other step and take double-sized steps, which is obvious. And I'm going to keep doing that. I'm going to then, jump over, bigger steps and make those double again. And if I do this some number of times until I'm left with roughly 1 over epsilon steps, I'm left with an epsilon n approximation, which is an immediate exercise you can go through. But so the way I want to think about this is actually I'm going to look at the original function that we had, which is the sum of all those functions. And then my approximation was every other step but double the size. If I subtract the two, I see that the error or the discrepancy between those two functions is just the sum of the original functions multiplied by either 1 or minus 1. And so if I look at this discrepancy function, if I look at the signs that I get from my steps or my jumping steps, quote unquote algorithm, then I see the discrepancy function is incredibly flat. And then I want to ask myself, if I have for this step function, I know the discrepancy is very small. Does that always lend itself to small corsets? And the answer, of course, is yes. Otherwise, I wouldn't be standing here. So the fact that you can always create corsets of size, if you have the what we call the class discrepancy, which is this minimal. If you have a set of functions, a set of points, if you have look at the minimal signing of those functions and try to get the flattest possible function, the magnitude of that function is the class discrepancy. You always get small corsets, and the construction is also extremely simple. You basically keep pruning the data in the same way that we just did now, but you also get streaming algorithms and deterministic and randomized streaming algorithms that are almost as small. Now, most of this work, or at least most of these ideas, are not incredibly new. Some of them were known in this way or another. I don't think they were put together in quite this way. But the question that I want to ask myself is how to generalize this, or how to compute the class discrepancy. In one dimension, if we look at instead of a step function, we look at like a slightly smoother step function, you wouldn't be shocked that doesn't break things, and you can still get the discrepancy being something like a constant over m, which is the same thing you got for this step function a second ago. Neither does pretty much any kernel in one dimension. So any bump function, any bump-like function would have this same thing. But if you take this to higher dimensions, then suddenly things break. So if you look at this like sigmoid activation regression, we didn't know how to bound its class discrepancy, and neither could we do it for Gaussian kernel until we start working on this problem. So a high-dimensional version of a bump is like some kernel function. Here is the Gaussian kernel. And you'd think to yourself, I'd want to maybe think about, so this expression, the class discrepancy, actually is incredibly similar to the Rademacher complexity. Instead, the only difference is that instead of looking at the expectation of these like random signs, we look at the minimal possible assignments of random signs. And, oh, yeah, okay. So there was an animation here. So I was supposed to, I was trying to say, are those similar? And then the nope would appear. They're not similar, okay. And there's a typo. It should be R, capital R, underscore M at the bottom. But the Rademacher complexity generally goes like something like 1 over square root M or square root N, depending on your notation. And the class discrepancy usually goes like 1 over M, which gives you much smaller corsets than you could get by sampling. But also the math behind it kind of ends up being very different. So as an example, I want to kind of state an obvious thing that everybody knows, that if I have a set of unit vectors, if I sum them up with random signs, I will end up in a ball of radius roughly square root n. That's like the random walk distance, right? But if I try to end the walk as close as possible to the origin, I can always find an assignment of signs that actually is contained in a radius square root d, which is potentially much smaller. Doing this, of course, is much harder. You have to solve an LP to get those signs. But this becomes much harder in general if you sum up matrices with arbitrary signs, and now the norm is not just a distance, but it's like the 2 norm. How do you, what's the best you can do? And apparently you can get this distance square root d, but that's hard to do. And the main technical lemma in our paper shows that if you take any set of vectors, if you look at the sum of the vectors or the sum of the covariance of those vectors or the sum of their outer products, like as a 3 tensor, 4 tensor, and so on, you can simultaneously make sure that, you can find signs that simultaneously make sure that all of those are small in 2 norm, which is a kind of to us was a pretty surprising result. But the interesting thing is that it seemed like a detour to talk about those sums of matrices and tensors. But in fact, that's all you need for any function that is a function of the dot product in some Euclidean space. So that includes the Gaussian kernel and the sigma activation losses and all these things, because you can just expand in the Taylor series, kind of linearize things that linearize the dot product, which becomes a tensor, and then things just fall out. So this is the entire transition. So basically, everything was contained in the last result. And this is that. This is my 1 minute. My 1 minute. So what you get is basically for a bunch of problems, including logistic regression, sigma activation regression, covariance estimation, graph Laplacian approximation, Gaussian and other kernel approximations, and so on. You get that all of them have corsets of size square root d over epsilon, and have streaming algorithms for creating those corsets. Specifically for kernel density, we actually closed an open problem that's been worked on for about 10 years now, or maybe more. And while I think this is incredibly, to me, surprising result, there's still a lot of work to be done. First of all, we started with the step functions and the CDF. The high dimensional analog of that is a 0-1 classifier. We don't know what the class discrepancy is for that. Neither do we know what the class discrepancy is for any kind of non-smooth or non-differentiable kernels. And so a lot of things, so are those fundamentally different, or are just our math breaks? We have no idea. And a second, maybe more fundamental question is, can we compute those things? So we know they exist now, but we don't have great algorithms to actually find those asymptotically optimal corsets for any of those problems. That's it.
Time for one question while the next speaker sets up.
Yeah. No, it's a kind of a strong condition. If you're going to do ERM on your corset, then you can oftentimes. Yeah, you can cook up some things like that. Yeah.
Let's thank the speaker again. The next talk is on optimal average case reductions to sparse PCA from weak assumptions to strong hardness by Matthew Brennan.
Hi. So this is joint work with my advisor, Guy Bresler. So I'll be talking about average case reductions from Planck-Leak to sparse PCA. So the focus of this talk will be on the sparse PCA detection problem, where you observe NIID samples, which under the null hypothesis are from a standard D-dimensional Gaussian, and from the alternative hypothesis are from a D-dimensional Gaussian spiked in a sparse direction V. Throughout this talk, V will denote the sparse direction, N will denote the number of samples, D the dimension, K the sparsity, and always we will view V as uniformly at random chosen from a natural distribution, like the set of all unit vectors with non-zero entries, plus or minus 1 over root K. Also, K will always be thought of as much smaller than root D. So this model has been very well studied, and it's known to be information theoretically impossible if the level of signal theta is much smaller than square root K log D over N. On the other hand, polynomial time algorithms only begin to work when theta is at least square root of K squared over N. So there's this K to K squared gap. One remark I'll make is that generally people consider the estimation version of this problem, and for us, detection implies hardness of estimation up to L2 error theta. So when you try to show lower bounds against polynomial time algorithms, you need to make some sort of complexity assumption. So the complexity assumption we'll focus on is Planck-Clique. So the Planck-Clique problem, in the Planck-Clique problem, you observe a graph G with n nodes, and the task is to determine whether or not it's sampled from an Erdős-Rényi random graph with edge density half, or one where there's been a K-clique planted uniformly at random in this graph. And even though the Planck-Clique becomes the largest clique in the graph as soon as K exceeds 2 log n, it's only when K exceeds about root n that polynomial time algorithms for Planck-Clique begin to work. So the Planck-Clique conjecture is that this is optimal, that you need K at least root n for PC to be solvable. So just to state very concretely the goal of this talk is we're going to be focusing on reductions which begin with a hard instance of Planck-Clique, so one with K smaller than square root n, and map to an instance of sparse PCA just below the conjectured computational limit of square root of K squared over n. And these reductions have to work in polynomial time and need to map the corresponding hypotheses to one another within little o of 1 total variation distance. Why this setup? Because total variation distance will allow any test for sparse PCA with type 1 plus 2 error epsilon to correspond to 1 with that same error for Planck-Clique. So there have been a number of previous reductions from Planck-Clique to sparse PCA, beginning with a Colt 2013 paper of Berthet and Regularized, and with several others following after. And all of these reductions either map to, they show hardness for algorithms that run in polynomial time and are robust to the noise distribution of the model, so not quite the spike covariance model that we're considering here. Or they show lower bounds at a suboptimal rate of theta is K squared over n rather than square root of that. So our first main result is a reduction which resolves both of these issues simultaneously, mapping to the spike covariance model and at the optimal rate of square root of K squared over n. So this is just a brief overview of how the reduction works. We begin with Planck-Clique, and then we apply an average case gadget that asymmetrizes the adjacency matrix in Planck's diagonal terms. We then have another gadget to Gaussianize this data matrix. And the key step is to sample a rotation matrix from the Haar measure on the orthogonal group and rotate each of the rows of the data matrix by this rotation matrix. And this spreads the signal out and actually exactly maps the distribution of this Gaussianized Planck-Clique to the spiked covariance model. And then we just have some post-processing steps with subsampling and padding. So if you analyze this reduction, you can show that the signal level that we arrive at is big K over square root of n, where K and n are the parameters of the Planck-Clique instance, times the optimal rate for sparse PCA. So basically what this means is that if we can start with an instance that's about K is root n, then we've shown exactly the result we want. But what if you ask the further question that we start with some suboptimal instance of Planck-Clique? So maybe K is n to the 1/3. Then if you plug this into the rate here, turns out you show nothing beyond the information theoretic limit, so no non-trivial hardness. So the second question we try to answer is, what if we just are willing to only assume the Planck-Clique conjecture for some incredibly small size of Planck-Cliques, so like maybe polylog n or something like that? Can we show any non-trivial hardness? And the answer is yes, and it's based on two observations. So the first observation is that all previous reductions treated the Planck-Clique data matrix as the samples for sparse PCA in one way or another. And this is wrong for several reasons, but it's most obviously seen by by noting that the empirical covariance matrix is much more closely aligned with a planet-clique instance. So if you scale and shift the empirical covariance matrix of a bunch of sparse PCA samples, you can see that it's equal to like theta root n over k times some block of ones plus a noise matrix with order 1 fluctuations. And note that this looks like a planet-clique instance exactly when theta root n over k is approximately 1, which is exactly the optimal rate for sparse PCA. So this gives us our new reduction idea, which is instead mapped to this scaled and shifted covariance matrix, and then from there get to the samples. But this comes with an issue. So the issue is that there are really complex dependencies among the entries of the empirical covariance matrix. And our average case reduction techniques seem to really need independence among entries of data matrices to map to them. So the way we overcome this is with a random matrix theory result of Bubeck et al. So it turns out under H0, these dependencies disappear if you start with a sufficiently small planet-clique instance. And under H1, you can maneuver with this theorem to show that actually the dependencies become Gaussian in nature. And so in particular, you can decompose the empirical covariance matrix into the sum of 4 Gaussian terms. And the key observation is that these 4 terms have meaning. The first is just noise, but the second 2 are actually very, very weak instances of sparse PCA themselves. And then the third one is just an elevated submatrix. So putting this all together, we can arrive at our second main reduction, which first we have a gadget to clone planet-clique and have 3 instances of planet-clique. And then we map them to each of the terms that appeared in the previous structure theorem. So the first one is, the first problem is a Gaussianized version of planet-clique, which we can map to just like we did in the random rotations reduction from earlier. And then the second 2 are very weak instances of sparse PCA. So we can actually take the previous reduction and plug that in to map to the second 2 problems. But the thing though is that these are so weak that they're below actually the mapping to something below the optimal rate is totally fine because all of the signals captured in the first problem. Then just add up all of these terms and you arrive at something which under both H0 and H1 is distributed as the empirical covariance matrix of the spike covariance model. And then now our final step is to sample a random orthogonal matrix from the Haar measure and then take its top rows and then rotate the empirical covariance matrix by this rotation, like these top rows of rotation matrix. And you can show that this exactly samples the distribution we want. So putting it all together in a theorem, we show tight hardness for sparse PCA assuming k is much smaller than square root of n in the planet-clique conjecture. And that's it. Thank you.
We have time for a couple of questions.
So the random matrix theory results analyzes when a GOE matrix converges to a Wishart matrix. So for a Wishart matrix, you have 2 parameters. You have the dimension of the samples, and then you also have the actual dimension. Sorry, the number of samples and the dimension. And if the number of samples is sufficiently high, then you're adding up a bunch of independent terms, and it eventually Gaussianizes to a GOE matrix. And they characterize that rate.
Yeah, I have a question.
Sure.
Is there a reduction in the other direction?
So currently, no. Like, we don't know of a reduction. But I think it should be closely related to this random matrix result. Yeah. Yeah, but we don't have one. Thanks.
So let's thank the speaker again. He's going to give the next talk as well. The next talk is also by Matthew Brennan on universality of computational lower bounds for submatrix detection.
So I'm back. And this is joint work, again, with my advisor, Guy Bresler, and with Wasim Halehel. And so this talk will be on universality of lower bounds, and also based on the planet-clique conjecture. So first, let's consider two problems. Biclustering and the detection of a single hidden community in sparse graphs. So biclustering is, again, a detection problem where under the null hypothesis, you observe a matrix of IID Gaussians, centered Gaussians, and under H1, you observe the same matrix, but now with an elevated mean along a k by k principal submatrix. Now, this model's been studied extensively, and its information theoretic limits and computational barriers have been characterized, also characterized based on the Planet-Clique conjecture. And the community detection problem, in the community detection problem, you observe an n-vertex graph G, and the task is to decide whether or not it's been sampled from a sparse Erdős-Rényi random graph. Here, think of Q as tending to 0 rather quickly, like polynomially in n, or if it's been sampled from this graph with a k-vertex subgraph planted with twice the edge density in the rest of the graph. And again, it's been very well studied and characterized. So in particular, papers by Ma Wu, Hayakushu, and our Colt paper last year characterize that the Planet-Clique conjecture implies that the computational barriers listed here are exactly the computational limits. We have both corresponding upper bounds and lower bounds. So if we plot if we divide the parameter space into three regions, the regions in which the problem is information theoretically impossible, PC hard, and can be solved in polynomial time, we arrive at suspiciously similar plots, like identical plots. And here, the x-axis is the sparsity k plotted on a log scale, and the y-axis is 1 over the signal, also plotted on a log scale. So this raises a general question, like how universal is this statistical computational gap, and in particular, the phase diagram I just showed you. So both of these problems are very closely connected to the general submatrix detection problem, in which you observe a matrix M, which is n by n, and the task is to decide whether or not it's pure noise, so its entries are IID sampled from some distribution Q, or if it's that same distribution with a planted principal k by k submatrix of IID samples from another distribution P. So the question we seek to answer in this talk is for what distributions P and Q, like generally over some measure space, can we characterize the statistical computational gap through average case reductions from the Planet-Clique conjecture? So there's been a plethora of work on universality of information theoretic limits and of algorithmic guarantees. But to the best of our knowledge, this is the first universality principle for computational lower bounds. And one remark I'll make is there's something surprising which emerges from the reductions in this work, which is that in general, the difficulty of average case reductions is mapping to a particular distribution. That's usually what the technical difficulty arises out of. And here we have to sort of do this in a strong sense. We have to map simultaneously to many, many different distributions in order to obtain a universality principle. And somehow this ends up being almost technically easier than in the information theoretic case, which is somewhat surprising. So first, before we proceed to state the results, we need to identify some assumptions on P and Q. So the goal is to identify a statistical computational gap in the general submatrix detection problem as a trade-off between NK and some notion of signal between the two distributions P and Q. So what is the right notion of signal? Well, it should be something like how easy is the classical binary hypothesis testing problem between P and Q. So consider the classical setup. Neiman-Pearson tells us that the optimal test is thresholding the log likelihood ratio. And a classic analysis with Chernoff bounds shows that the type 1 plus 2 error of this test is upper bounded by e to the minus m e sub p tau plus e to the minus m e sub q tau, where tau is the threshold in the log likelihood ratio test. And e sub q here is a standard Chernoff exponent. So it's the Legendre transform of the log likelihood ratio between P and Q. So just to summarize the previous slide, we'll define a pair P and Q to be computable if it satisfies a few simplifying assumptions. So P and Q are mutually absolutely continuous. They have finite KL divergences. There is an oracle that outputs a sample from Q in polynomial time. and there's an oracle computing the likelihood ratio between P and Q in polynomial time. This is necessary for like information theoretic upper bounds and algorithmic upper bounds. And to summarize what we thought from the binary hypothesis testing setup, the measure of signal that we'll have is the symmetric KL divergence between P and Q, and also these Chernoff exponents. Because you can think of the symmetric KL divergence as some notion of the signal, and then E sub P and E sub Q are just notions of concentration around the signal. In particular, lower bounds on E sub P or E sub Q correspond to large deviation principles for the log likelihood ratio. Okay, so now we're in a situation where we can state our main computational lower bound. Suppose P and Q is a computable pair, and the KL divergence between P and Q is much smaller than n squared over k to the fourth if k is larger than root n, and we have a large deviation principle, in other words, a lower bound on E sub P. Or we're in the low sparsity regime where k is much smaller than root n, and the KL is just basically below a constant. Here, little p denotes the density in the Planet-Klick conjecture. And we also, once again, have a large deviation principle. Then the Planet-Klick conjecture implies that at edge density p, the PC conjecture implies there's no polynomial time algorithm solving the general submatrix detection problem. So that is a bit of a mouthful of a theorem, and we're going to simplify it in the case where we have something weaker than a sub-Gaussianity assumption on the log likelihood ratio. So here are some technical conditions which are on P and Q, and under these technical conditions, which are actually much broader than they appear. They're all weaker than sub-Gaussianity of the LLR. We recover the same diagram as from biclustering and for single community detection. So here I'll just give a brief sketch of how the reduction works. So we begin with a Planet-Klick instance, and then we embed it as a principal minor in a slightly larger matrix, and plant diagonal entries. One technical remark I'll make is that even though they seem somewhat trivial, getting these diagonal entries and then asymmetrizing ends up being a fairly important technical obstacle for these reductions. Like previous work for biclustering and community detection, the main analysis went into analyzing the repercussions of these diagonals as you pass them through their reductions. So once we perform that gadget, now we apply something called that we term multivariate rejection kernels, which are just a rejection sampling based technique for sampling these product distributions. And the idea is that we can construct a simple map based on rejection sampling that sends ones to L by L submatrices of IID samples from P, and Bernoulli P to the same for Q. And as a result, we end up with the matrix we want, and we've now dilated it by a factor of L. And it turns out that that exactly the loss in KL that you get from applying these MRKs ends up trading off exactly with the increase in sparsity and the increase in dimension from L in a tight way. And thank you. That's it. So it does not. So that actually is the perfect example actually for this talk, because that's an example of P and Q that doesn't fall under this phase diagram. It falls under the problem of general submatrix detection, but like you're talking about the log density threshold. Yeah, so that yields a different diagram. And so having a universality class that captures that would also be like an interesting open problem.
Any other questions? So let's thank the speaker again. So the next talk is on reasoning in Bayesian opinion exchange networks. Is P-space hard? And Jan Hasla will give it on.
Okay, so this is joint work with Ali Jadbabaye, Elhanan Mossel, and Amin Rahimian. And our result is a computational hardness of something, and this something is reasoning in Bayesian opinion exchange networks. So let me start with some high-level motivation, and that is Aumann's agreement theorem. So this is a statement that says that Bayesian agents with common priors and common knowledge cannot agree to disagree. And if you think of it as a mathematical statement, it's almost a tautology, but it is considered interesting because the predictions of this theorem do not accord with observations, right? There is a persistence of disagreement in the real world. And in particular, people disagree about why that is the case. And the punchline of our work is that we suggest that in presence of network structure, there might be a computational infeasibility. Okay, so before I explain the model, let me give a quick motivation of like why it is going to look like it does. So this is a model that is studied in the economics literature, and it concerns a group of agents that try to aggregate or learn a simple piece of information. And we want them to be arranged on some sort of social network. We want them to be fully rational, honest, and act by exchanging some sort of natural summaries of their knowledge. So how does it look like? Well, there is a state of the world, and this is just a bit. Okay, so this is a piece of information that the agents are trying to learn, and it's a uniform random bit. And then there is a group of agents arranged on a graph, directed graph. And we adopt a convention that if there is an edge from U to V, then that means that agent U will observe the actions or opinions of agent V. And then before the process starts, each agent U receives a private signal, which is, again, it's just a bit. Okay, so state of the world is bit, and this F and T denotes false and true. And the private signal is a bit, 0 and 1, and the formula is not important. Like, think of it as a noisy version of the state. Okay, so for example, with probability 3/4, each agent independently sees theta. With probability 1/4, it will be the opposite of theta. Now, after seeing the private signal, there is a dynamics, and this dynamics proceeds in discrete time steps. Okay, so we have time t0, 1 equal to 1, 2, and so on. And in each time step, each agent broadcasts an action to its neighbors. And this action is, again, a single bit, and it is meant to be which of the two states the agent considers more likely at the moment, according to its Bayesian posterior. Okay, so more formally, if I am an agent at time t, there is some knowledge that I have up to this point. So what is this knowledge? We call it observation history. It's my private signal, and it's the actions of all my neighbors that I observed at time steps t prime strictly less than t. And now my action at time t is just which of the states of the world is I consider more likely. So it is true if and only if the probability that theta is true given my observation history is greater than 1/2. Okay, and we make an assumption that the prior and the structure of the network, all the probabilities are common knowledge, and the agents are honest and fully rational. Okay, so to get some idea, let's think of the first couple of time steps of this protocol. So at time equals 0, which is not on the slide, it is very simple. All I know is if I'm an agent, all I know is my private signal, and this is just a noisy version of theta, so I just output my guess according to the signal that I saw. At time equal 1, I observe the actions at time equals 0 of all my neighbors, and I know how they arrived at their actions. They just output them according to their private signals, so I also learn the signals of my neighbors, and since those signals are conditionally independent, again, the formula is not important, but it's a relatively simple computation, again, to make a guess at time equal 1. However, at time equal 2, it becomes more complicated, because then I observe the subsequent action of my neighbors. These are based on actions of their neighbors, and now there might be overlap in those neighborhoods. At later times, there might be cyclical dependencies, so it seems to become more complicated, and actually it does, and we showed it already at time 2, it is NP-hard. And so, as I said, this model does not come out of nowhere. It's studied in the economics literature, and there is a lot known about it. In particular, it is sensible in that this Aumann's agreement, with some caveats and under assumptions, this Aumann's agreement holds in the model. So the agents converge to the same action as time goes to infinity. And also, you can show that the actions on which the agents converge is equal to state theta, with probability that goes to 1 as the number of agents grows to infinity. And economists know that this model is hard, and what we do is we try to make a more formal statement about this hardness. Okay, so to prove hardness, we need some decision problem. So our decision problem is from the inside perspective. Okay, so think you are an agent in the network, so you know all the details of the network, you know the time, and you know your observation history up to this time, and your task is to output the action, so output the guess for the state. And to explain the result, I also need a notion of belief. So this is just my Bayesian posterior. Okay, it's the probability of the theta equal true given my observation history. So the theorem, at least the NP-hardness theorem, just says that we have a reduction mapping a FreeSat instance to a Bayesian network at time equal 2, such that if the instance is satisfiable, then the posterior of the agent at time 2 is exponentially close to 1. And if the instance is not satisfiable, then the posterior is exponentially close to 0. So in particular, if the posterior is very close to 1, you should output 1. If the posterior is very close to 0, you should output 0. So that also implies that computing this binary action is NP-hard. And note that this result is robust in that it shows that it's hard, but not in a spurious case where the posterior is very close to 1/2. It's already hard to distinguish between two posteriors that are as far away as possible, that are almost as far away as possible. Okay? And then it turns out that we can improve it to p-space hardness. That is, we can show that there is a polynomial time reduction where we can substitute SAT, which is this canonical NP complete language, with TQBF, which is a canonical p-space complete language. And then we can show that if we have a TQBF instance, which is a logical formula with k quantifier alternations, then we can reduce it to a Bayesian network at time equal to k, where if the formula is true, then the posterior at time to k is exponentially close to 1, and if the formula is false, then the posterior at time to k is exponentially close to 0. And in particular, if then you take time being polynomial in n or linear in n, that implies that the computation of this of binary action is p-space hard. Let me skip that. So as a final comment, one weakness and I think an interesting open problem that we have is that our result is worst case in that we just show that there exist configurations of those private signals for which the computations are hard. There exist configurations of observations for which the computations are hard, but they arise with an exponentially small probability. So we do not exclude the existence of algorithm that works with every network on average over the probabilities of private signals. On the other hand, the result is pretty robust in that we have this hardness of approximation aspect. And also, I mean, you can think of tweaking this model in many respects. And as far as we can see, like, at least some sort of hardness persists for most of reasonable tweaks you can make. Okay, thank you.
Guesses for maybe structured instances where you think it might be much easier? Some structured families it might be.
Right, so there is one very interesting case where actually the computations are known to be easy, and this is when the signals in the state of the world have joint Gaussian structure. So this is actually a paper from 2016 by Moser, Osman, Tammuz, and it's yeah, like it's actually quite surprising. You do some linear algebra, and it turns out to be feasible. But yeah, I think these are like very special cases, but that's one example.
Let's thank the speaker again.
Sounds
The
good.
next talk is on sum of squares meets square loss, fast rates for agnostic tensor completion, and Dylan Foster will give the talk.
Thanks. Cool. Yeah, so this is a talk about efficient algorithms for tensor completion in the agnostic model. It's work with Andrei Ristevsky. So let me describe the problem. So in tensor completion, we have an unknown low-rank tensor, and our goal is to recover the tensor from a small number of observed entries. Okay, so for this talk, when I say an unknown tensor, what I mean is, just a d by d by d array, so like a 3 tensor. And by low rank, we just mean that it decomposes as the sum of a small number of rank 1 components. So, if you're familiar with the classical matrix completion task, this is just a natural higher order generalization. But we're actually going to depart from this model a little bit in this talk, and what we'll work in is the agnostic version of the problem. So here, instead of assuming the tensor is low rank, we make no assumptions, but we would like to predict the entries well, as well as the best low rank tensor. So what this means, is if y does turn out to be low rank, we'd like to have good error. If y is complete noise, maybe we won't do so well, and in general, we hope to get like a nice interpolation between these two regimes. So the way we'll formalize this is as a special case of a general tensor regression framework. So here we're going to get n feature target pairs IID, and features for us are just d by d by d tensors. And for any particular tensor, we'll just measure risk via squared prediction error for the targets. And what we'd like to get is an excess risk bound. So we'd like to produce a predictor t hat where its loss is small relative to the loss of the best rank R tensor. Okay, and the tensor completion setup, this is just a special case of this where the observations are just random indicators for the entries we've observed. Okay, so let's first look at what rates are possible for this setting. And here it's first helpful to think about what's just possible information theoretically. So here, if we focus on the case where rank is 1, it's well known that there's an inefficient algorithm that gets a rate of d over n. So d is sort of the natural parametric rate, and we expect a 1 over n rate because we're working with square loss here. But when you go for efficient algorithms, things get a little bit more interesting. Here it's helpful to think about what happens in the matrix case. So in the matrix case, you can do least squares with a nuclear norm penalty, and this allows you to kind of have your cake and eat it too. So you get the d over n rate, and you get this with an efficient algorithm. But unfortunately for tensors, as soon as you go above, order 2, the tensor nuclear norm is computationally intractable, even to approximate. And so, we need to think about other algorithms. This approach won't work. One natural thing you can do is just reduce to tensor completion by flattening your tensor, but this gets worse dependence on d. So this gets d squared, and that's sort of like a natural barrier for matrix completion methods. But interestingly, Brock and Moitra in 2016 showed how to get beyond this barrier. So they give a rate that becomes non-trivial as soon as n is at least d to the 3 halves. Okay, so that's better than d squared. And interestingly, it's probably unlikely that you can get better than d to the 3 halves under standard hardness assumptions. But what you notice about this bound is that it's what we'll call a slow rate. So if you look at the inefficient algorithm, this was going down as 1 over n. And this one is only going down at a rate of 1 over root n. So our main contribution is to give an efficient algorithm that gets the natural fast rate analog of this result. So we get a rate of d to the 3 halves over n. So in a little bit more detail, our main theorem is the following. So we show that if you do least squares with a constraint based on a sum of squares relaxation for the tensor nuclear norm, then your risk relative to the risk of the best rank R orthogonal tensor goes as d to the 3 halves over n with a polynomial dependence on R. At a more conceptual level, sort of the key thing we show here is how to make sort of the usual like localization arguments that are used to prove fast rates in high dimensional statistics. We show these play nicely with the sum of squares relaxations. So basically, whenever you try and prove fast rates for convex relaxations, sort of the key abstraction to think about is what's called localization. And essentially what this is it says that if you, when you're proving generalization error bounds, you kind of only need to look at tensors that are close to the optimal predictor. So we show how to make these arguments work for, for SOS in this setting, essentially. And beyond this, we show how to extend this to some other measurement models, and we also give another hardness lower bound, which essentially just says that if you believe standard CSP hardness assumptions, you probably can't improve this d to the 3 halves factor by much. Okay, so in the remaining time, I'll just talk about the algorithm and its analysis in a little bit more detail. So the starting point for the algorithm is to look at the tensor nuclear norm. And this is essentially just looking at what is the minimum weighting that allows us to write our tensors as sum of rank 1 components. But it's a little bit more helpful to think about this just in terms of the dual norm, which is the injective tensor norm. And that's really just the operator norm for the tensor as an operator on rank 1 tensors. So this is intractable to compute, but what you can do is the sum of squares relaxation. And all you really need to know about this for this talk is that sum of squares defines a sequence of relaxations of the norm, the injective tensor norm, parameterized by a degree k. And so these approximations get tighter as k gets larger at the cost of more computation. So our algorithm is just least squares subject to a constraint on the dual of the injective tensor, or of the SOS injective tensor norm. This is what I call the SOS nuclear norm of degree k. So how do you analyze this? So let's define T star to be the best fitting rank R tensor, and we'll define script T to be a set of what we'll call like feasible estimators that come out of our least squares procedure. So these just have small SOS nuclear norm relative to T star. So there's two parts. So the first part is to show that your generalization error is bounded by what's called like an offset Rademacher process. So this has one term that looks like the usual kind of uniform convergence, but it has a negative quadratic offset that's sort of trying to cancel this statistical deviation term. And so we want to show that it cancels it enough. And this is where we need new arguments for SOS. And this is really where this idea of localization I was talking about comes in. So there's 3 steps. And so the first step is just to observe that this Rademacher term scales as sort of like a statistical term times the SOS nuclear norm of the difference between the tensor we're considering and the optimal tensor. And the difference in subscript here from 6 to 4 is intentional. So the second step is to give what's called like a norm comparison inequality. So this is a new lemma. And so what we show is that for the feasible tensors that arise here, you can pay a factor of rank to move from the SOS nuclear norm to the Frobenius norm. So it says in a certain sense, the feasible tensors are approximately low rank. And then the third step is to give what's like called a restricted eigenvalue guarantee. And this shows that if you look at the Frobenius error here, this is proportional to the empirical squared error. So if you chain all these inequalities together, what they say is that this first Rademacher term arising in our generalization bound, this is basically proportional to the offset term, and so you get a cancellation, and this leads to the 1 over n rate. So let me just describe these technical tools in a little more detail. So there's 2 tools. The first is this norm comparison inequality, and the second is this restricted eigenvalue guarantee. And we're sort of most excited about the norm comparison here because this requires a new characterization for what does the subgradient of the SOS nuclear norm look like. So that's sort of like the key tool, and I imagine this may have applications in other settings. So once you have this, you can prove this restricted eigenvalue guarantee essentially by using concentration guarantees we already had for the SOS nuclear norm, plus some sort of standard peeling arguments, and by using this norm comparison itself. Okay, so that's the result. To summarize, we have the first efficient algorithms that beat this d to the squared barrier for agnostic tensor completion and get the fast rate. And these are via some new geometric inequalities for SOS. But sort of conceptually, the main takeaway here is that like these SOS relaxations, these play nicely with the usual high-dimensional statistics analysis, and I think it'd be nice to see the extent to which this works for other models and other relaxations. So thanks.